So in this session on signals and systems, we are going to study the correlation operation between two signals. So let us start. So as we have said, two signals are involved in the correlation. And what is the significance of calculation of correlation? Significance is that the value of the correlation will give you some idea about the similarity between two signals. So the correlation measures the degree to which the two signals are similar. So what we are going to do in this session is to see the maths which will allow us to do the calculation of correlation. But in our later session, we shall see the application of correlation. So its significance in engineering will become clearer. Okay, so let us start. So let us first of all start with continuous time energy signals. Since the correlation is defined differently for energy and power signals, we have to take those two cases separately, and we first consider continuous time energy signals, and let us see the definition. So let's say xt and yt are given to us as functions of time, and we have to calculate the correlation. So what we do, we take xt, then delay yt with respect to this by tau seconds, take the product, integrate over all times, and the expression that you get clearly will be a function of tau from the normal knowledge of mathematics. Because you can see, if you look at the product will be a function of t as well as tau. But we integrate with respect to time, with respect to t, and then when you put the limits, clearly the remaining function will only be a function of tau, and that is called as rxy tau. Okay. Now in this case, we have said xt was our reference and yt was delayed. Another way of saying the same thing would be, take yt as your reference and consider that xt is advanced by tau seconds. So you can write it in this form: rxy tau is xt plus tau yt dt. Whether you do this calculation or you do this calculation, both are going to be similar. But suppose we change the order here. So instead of taking rxy tau, suppose we take ryx tau. So like we did in the first expression, here xt we started with our reference of xt. Here, since y is the first variable, we take yt and then delay xt by tau and then calculate this. So when we do this, it will be easy to show how these two are related, that is rxy tau, and how it is related to ryx tau. In order to show this, what we do is ryx tau, from this expression we obtain the expression for ryx minus tau. So this is minus tau, so this becomes t plus tau. Now if you compare this right hand side with this expression, you will find that the right hand side will be rxy tau. So this tells us that rxy tau is equal to ryx minus tau. This means that one correlation is the folded version of the other correlation. Depending on which signal you take first, you get these two different correlations. Alright. So that was for continuous time. What about discrete time? Discrete time, rxym, again product xn into yn minus m. Remember, for the continuous time signals, time is our real variable. But for discrete time signals, n is an integer. It's not a real variable. And m is a delay, which also is in terms of number of samples. So one sample delay, two sample delay, and so on. Okay. So you take the product of this, and instead of the integration for continuous time signals, for discrete time you sum up all these values. Similarly, ryx m will be yn into x of n minus m, and exactly analogous to what we did in the case of continuous time signals, we will be able to show that rxy m is equal to ryx of minus m, folded versions of each other. Alright. So let us now take a specific example. Suppose xn is 1, 2, 3, and this arrow says that this corresponds to n equal to 0. So this will be n0. So instead of showing the values of n separately, sometimes this convention is used. The arrow corresponds to n equal to 0 position. So all others can be calculated, because if this is 0, this will be n equal to 1 and this will be n equal to 2. Then yn is 369 and this is also starting at n equal to 0. And we want to find out the correlation between these two sequences for various values of delays. That is what we want to do. So this is our expression. So what we do is, first we start with 0 delay, so m equal to 0, and do our calculation. So let's look at this. If m is equal to 0, then yn is not shifted at all, and these two sequences are completely aligned with respect to each other. So m equal to 0, xn is 1, 2, 3 here, yn minus m is 0, so this is clearly same as yn, so that is 369. And now you take the product of individual components, so 1 into 3, 3, 2 into 6, 12, 3 into 9, 27, and finally you sum all of them. So you get 3 plus 12 plus 27, that is 42. So this is the value for correlation you obtain for m equal to 0. Then you take m equal to 1, so this yn minus 1 m will become yn minus 1, and this sequence will shift to the right. So 2 and 3 will get aligned with 3 and 6. So let us see that. M equal to 1, so these two are aligned now. This is 0, this is 0. So the significant values are 2 into 3 equal to 6, 3 into 6 is 18, so you get 24. Then m equal to 2, this shifts further, so only one value is aligned and you get 9. Beyond that, there is no point in computing, because then there is no overlap at all and you will get only 0 values. So now what you do, you shift yn to the left. That means you advance it by one sample and then see what happens. So m equal to minus 1. So this shifts to the left. So 1 and 2 get aligned with 6 and 9. So 1 into 6, 6, 9 into 2, 18. So 6 plus 18 is equal to 24. Then you again do it, advance it further. So these two are aligned and you get 9. So the final result is this: minus 2, minus 1, 0. Remember, these are delays. The correlation is a function of delay, function of m. Okay. And you find that all the correlated values are positive. That is because your first sequence, all values were positive, they were increasing. And the second sequence also, all values were positive and they were increasing. So we expect good positive correlation between them. And in fact, you get maximum correlation for value of delay equal to 0. This need not always be the case, but in this particular case it is so. Later on we'll see, if we take the correlation of the signal with itself, then of course for m equal to 0, this will always be maximum. Okay, let us now see how to write a MATLAB program for calculating the correlation. So this is our usual clear CLC, CLF. Then we define one sequence 1, 2, 3, 4, increasing in the positive direction, all values positive. Y is 2, 4, 6, 8. So two sequences are defined. So now you use a function which is available in the MATLAB called as a XCOR function. And this XCOR function accepts two input arrays. So X and Y it accepts, and it generates two arrays in the output. One is Z, which corresponds to the correlation between them. Incidentally, this correlation between two different signals is also called as a cross correlation. So this calculates cross correlation between X and Y and stores the result in the Z array. And the delay is stored in I. So once you have got this, then you can simply print the values of I and Z and also plot Z as a function of I. So it's easy to do that. This is just f print and this is just the formatting. So you will print I, all values of I, and you will print all values of Z. And also you will make a plot of I versus Z. So you use the statement stem IZ. Remember, it's a discrete function, so stem is better to use than plot. Then X label, Y label, title, grid on, and so on. So when you do this, this is what you get. You can see for all delays, you get positive correlation. Whether it is advance or delay, you get positive correlation, and you get maximum at delay equal to 0. And you can print out the values also, like in this. So when you run this program, these two will be the outputs from this. So as you can see, at delay equal to 0, you get 60, and then it decreases and decreases on the other side also. All right. So this was an example of a positive correlation. But let us see an example of a negative correlation. So you got 1, 2, 3, 4 increasing in the positive direction, all positive values, and Y has all negative values and increasing in the negative direction. So clearly when you take the sum of the products, you expect to get negative values, because positive value multiplied by negative value, you'll always get a negative value. So you expect that. But you get a negative kind of similarity, that is, this is increasing in the positive direction and this is increasing in the negative direction. So again, the rest of the program is straightforward. Zi, this is what you get. You can print the values and you can plot, and the plot I have shown here, although in the console you will also see the printed values here. So you can see in this case the correlation values are all negative. So that's an example of a negative correlation. All right. So let us now see a couple of sequences in which in one case you get a high correlation and in the other case you get a low correlation. So let us look at those sequences. So we are again discussing the MATLAB program for doing this. So clear CLC CLF. Let us say our x is given by this 1, 2, 3, 4, 5, 6, all positive numbers increasing in the positive direction. Y, all positive numbers increasing in the positive direction. So if you find the correlation between these two, x and y, you expect to get a good positive correlation. But suppose I define my y1 like this. Now you see, when I take the correlation between x and y1, I'll get low values. And what is the reason for that? Because there is not much similarity between x and y1. For example, if you look at the first two values, this is increasing from 1 to 2. This is also increasing, -2 to 4. So it matches the first time. But next, again, it keeps on increasing. From 2 it goes to 3. But here what is happening? From 4 it goes to -6. So it reduces. In the other case, this increases again reduces, and so on. So the pattern in this is quite different than the pattern in this. So you don't find too much similarity between x and y1, and that is why you expect the correlation to be low. So what we'll do is we'll calculate two correlations, one between x and y and the other between x and y1, and indeed show that in one case the correlation is high and in the other case the correlation is low. So what we do, first calculate the first correlation, put it in Z1, delay in D1, X core XY. Then calculate the other correlation, Z2, D2, X core X is same, but now second sequence is different, that is Y1. So you expect that Z2 is going to be small compared with Z1. So let us now plot these. So you plot, since you want to make two plots in order to compare them, use subplot 2, 1, 1, etc. So all this we have discussed before. So as far as the graphical plotting is concerned, you can just read through this and understand it. So let's look at the result. So here you get positive correlation between x and y. You can see here at delay equal to 0, the value is quite large. Typically it goes to about something like 180 and so. Whereas in this case, for delay equal to 0, you find that this is just exceeding 40. Okay. So, sorry. All right. So when you compare these two, basically you are showing that between x and y you are getting good correlation, but between x and y1 you are getting low correlation. All right. So in our next session, what we are going to study is the autocorrelation function and discuss an interesting application of this autocorrelation function. But for now, that's all.